Hi again, James. So these two questions. Didn't like 19. Didn't mind 20 actually. 20, weirdly enough, you start to see after a while, right? The integrals which they ask you in these papers, especially in the MAT and the Tamua, they're often not really integrals. They're often just like finding areas of like weird looking graphs because obviously that's what an integral graph does. It finds the area. So they're often not really about integration, and that's certainly a good example of that. And I quite like the modulus function because it's quite interesting to kind of analyze. But this one, it's just begging to be done naively. I don't know if you did something similar, but can I just show you what I did first? I was like, okay, S, and then what is that? 1 plus S, 1 minus S, so that's 1 minus S squared. Obviously, my S's are standing for sine and cos here. Plus C, 1 minus C squared. Oh, and I've forgotten the square root, yeah? So to the half. Yeah, I'm sure you realize you can put those in square root. So I've got 1 plus S times 1 minus S, that's 1 minus S squared. It's all in the square root. That's obviously squeeze C squared, square rooted is C. So you get SC plus SC. So you get 2SC. Yeah, and remember these are equaling 0. That's terrible notation. These are equaling 0. And so you end up with 2 sine x cos x equals 0, or theta. It should be theta really. And so sine 2 theta equals 0. And so 2 theta equals 0, 180, 360, 540. Oh, getting a bit ahead of myself. And 720. And then you can halve them all, So theta is 0, 90, 180, 270, 360. Yeah. Now I'm actually going to use this later on, so it doesn't hurt to do this now. But this is the naive approach. Now, what has gone wrong? Because what fault is there in the logic? Straight away you rule out 0 and you think 4, and it's wrong. Yeah. Because it's 19. Firstly, it's not going to be that easy if it's 19. And this did seem like pretty, it was almost like they were luring you into a false sense of security, saying, oh, you notice 1 minus sine squared is cos squared. That's all you really need to do. No, it's harder than that. So what went wrong? It's about the square roots. Let's talk about it like this. It's a square root bit where it goes wrong. So if I can just take us back to S root C squared, yeah, plus C root S squared equals 0. The reason why this is so dangerous, it's a classic case of extraneous solutions or missing solutions because there's square roots involved. Look at it like this, yeah? Can cos theta be negative? Yeah, it's negative for half the time it spends in its life, isn't it? Like it goes above the x-axis, then below the x-axis, then above, then below. So yeah, it's negative from 90 to 270 to be precise. Well, after you square it and square root it, it's no longer negative, if you see what I mean. Even though cos theta was definitely negative here, it's no longer negative. So when you say that equals SC, that is not true. Yeah, it's simply not true. To make the point a little bit clearer, because I do think this is a really, really, really important point. Cos theta can obviously equal minus a half. Yeah. Well, when cos theta equals minus a half, theta is going to be 60, and I'm just working out in my head, or one possible value of theta is 60, and sine of 60 is root 3 over 2. Yeah, so at the moment, like this should be evaluating to, if I was to follow this rule and do s times the square root of c squared, I'm going to get c squared is a quarter, square root I get a half times root 3 over 2 is going to be half times root 3 over 2 is going to be root 3 over 4. Yeah, so I just want to show you basically both things because we're saying that that equals that. Well, for these two values, the left hand side is going to be equal to root 3 over 4, but the right hand side is going to be equal to minus root 3 over 4. Do you see the point I'm making? That's nonsensical. That doesn't make sense. So clearly s times the square root of c squared has to be treated with extreme caution, yeah, because c can in fact be negative. What that does, I tell you what, it's another definition of the modulus, which we're about to do in a second. You can say it's x squared square rooted because it always returns a positive root that when it's written down, but it shouldn't because, like I say here, we've got to handle it with care anyway. We've got to handle it with extreme caution. Best way of doing it as well is to take values like carefully thinking about when sine's positive, when's cos positive, when's sine negative, when's cos is negative. That's what I'm going to basically do. So don't do that. Yeah, that is the mistake which they're crying out for here. It's the sort of mistake I would definitely make. I'm definitely not claiming that I would 100% get this right in an exam. I don't think I would. I think I'd be rushed. I'd be stressed out. I'd be happy that I'd found some solutions. And you have found some there. That is actually. It's not like this can't be true. This definitely can be true, and these are some solutions. But we're going to see why we actually end up with a hell of a lot more than that. So, okay, let's handle this with caution. Let's say firstly that we're just going from 0 to 90 degrees, because we can see, or 1 to 90 degrees if you like, because you can see well, that's the values we need to care about. Now here, S is positive and C is positive, yeah? Which means when you've got C and you square it and you square root it, that's fine, you get SC. And when you've got S and you square it and you square root it, it's fine, you still get CS, yeah? And so you're going to get 2SC equals 0 here, and that gives you all the same solutions as up here. So straight away we've got theta equals, I should ignore the 0 because we're going from 1, 90, 180, 270, or 360. Yeah, but what happens when we're going from like more than 90 to 180? Let's try not to have any overlap. I think when I did this in my notes, there was overlap. Yeah. Oh, I suppose it doesn't matter because we've already established 90 as a solution. But let's say we're going 90 and 180. 90 to 180. What happens there? Well, sine is still positive, but cos is negative now, yeah? Now, this brings us to the point over here. Now, how are you going to deal with s root c squared then? Are you going to call it sc? No, you need to call it the negative of sc to address the fact that there's a minus here to make that positive so that everything works out. So we're now going to say, okay, I know when I square root this, I'm going to have minus sc plus cs equals 0. This is clearly a tautology. It's always true, yeah? Like that is 0 equals 0. In other words, all values from 90 to 180 degrees are solutions. Yeah, purely because you're going to get, basically because you're squaring that negative. I tell you where it happens essentially. If you like, it happens over here when cos is like between 90 and 180. That's actually going to be a negative, but after you square that one and square it, that's going to be a positive. So you get SC minus CS, if you see what I mean here. You don't have to worry about sine because sine is positive from 90 to 180. Hope that makes sense, James. Do you see what I'm saying here? It's really subtle. I'm not saying I'd notice it, but that is what's going on here. So we get that, and if we run this logic all the way through 180 to 270, well, at that point S is negative and C is positive, yeah? And so what are we going to have? We're going to have, for the first one, well, that's just going to be SC, but for the second one, we're going to get minus CS equals 0, and that is obviously true all the way from 180 degrees to 270 degrees. Hang on. I've just realised that's nonsense. They're both, it's poor, isn't it? They're both actually negative when you're 180 to 270. Sorry, they're ones, yeah, let's just draw them. There's cos, and we're in this range, yeah, but here's sine. Let's get this right. My diagrams are so bad, aren't they? I'm gonna have to quickly draw this over here. Sorry, James. This is really poor. Yeah. Here, well, we can see that sine is going to be negative, but cos is actually positive. Oh, no, cos is negative as well. It is. Yeah, no, I'm just thinking in my notes. Did I get this wrong when I was doing it the first time? There, this is so poor. Cos looks more like this. Yeah, they're both negative here. God dear. Because you're basically down to here. You see what I mean? They're both negative down there from 180 to 270. Okay, so yeah, they're both negative and that's 0. So I was right the first time. Yeah, sorry about that. And then finally, you're going to get one positive and one negative to all. Oh yeah, but the problem is with this, when they're both negative, obviously we have to change the sign on both of them, and we get, yes, apologies, I've messed up my explanation here. 2 sine x cos x equals 0 again once you've changed the sign, and you get those again, yeah? So that's, big deal. We've already got loads of solutions. Finally, if I can actually get my causes and sines the right way around, sorry, James, 270 to 360 or 271 to 360. You're going to have sine is negative and cos is positive. So here you're going to get the minus, well, you're going to have SC minus SC equals 0. And so they're all solutions. So how many solutions have we got? We've got all of them from 90 to 180. Yeah. How many numbers are there, James? 91. That's the other place you can get proper caught out. How many numbers are there from 270 to 360? Although, to be fair, if you've been this careful so far, you're probably not going to make that mistake. You've got 91. And so how many solutions are there? There are 882 solutions, and you can check my answers there. I haven't actually checked them. Please do check them. But I think that's why the answer there is F. Didn't like this one at all. As in, actually, I wouldn't say I didn't like it. I thought it was a fantastic question, but what I mean is I wasn't up to it. I would have got that one wrong, no question about it. This one, I fancy my chances on a bit more because you just got to see the pattern of what's happening to the graph. Yeah, forget the integration. Think about the graph. Now, F1 is mod of x. It's going to be another case of me drawing some bad graphs, I think. Cool. You might think, oh, what's going on here? Well, we've actually got an area of 1, like, because you get an area of a half there because it's up to 1. You get an area of a half there. Okay, so F1, if you integrate it, would be 1. See if you can spot patterns, isn't it, really? What about F of 2? Well, because we've got a mod of a mod, it starts getting really kind of difficult to work out. You've got mod of x plus x. Yeah. Now think about if you had 0 to 1. Think about when things positive. Yeah. When it's 0 to 1, you can ignore all the moduluses. Yeah. I'm talking about on your graph when x is between 0 and 1. The modulus does nothing. Yeah. And so that's just going to look like 2x. Y equals 2x. It's basically going to be y equals 2x when you're working between 0 and 1. Yeah? But what about on the left-hand side, 0 to minus 1? Well, actually, it's going to be flat. Think about if x was minus a half. You'd do minus a half, and you'd make it positive, so that's a half. But then you get minus a half over here, and you get 0, yeah? The same thing's going to happen if you have minus 3/4 in there. It's going to become 3/4 minus 3/4. You're going to get 0. In other words, on the left-hand side, the graph's just completely flat, like that. Yeah. On the right-hand side, it's y equals 2x. But on the left-hand side, it's like that. When I saw that, I thought, it's got to be something to do with this question. Like, let's just try and figure out a bit of a pattern. F of 3 of x. What's that going to look like? Well, this is mod of x plus x, finish the mod, plus x, finish the mod. Yeah. What does this look like? Well, yeah, it's awkward, but once again, from 0 to 1, it isn't. It's just going to be y equals 3x. Because you know you're dealing with positive x's. What does the modulus do to a positive x? Nothing. Not a damn thing. So we're going to have positive x plus an x, that's 2x. Modulus still does nothing because it's still positive. Plus another x, 3x. Modulus does nothing, it's still positive. So this is just y equals 3x on the right-hand side. So it's just getting a bit steeper. And already I'm thinking they want me to find the area for f99 of x, and already I'm thinking this is just going to be y equals 99x over here. But it's this side which is worrying me. What's going to happen to this one? Well, look at this. When we've got this, we get, when we've got like minus a half, that's going to become plus a half, then it's going to become minus a half, so that's going to become 0, yeah? But then you're going to be doing minus a half modded, and then you're going to be making it positive, which is just a half. In other words, it's always going to return from minus 1 to 0. Yeah, I should write proper bounded inequalities here because otherwise it's going to get confusing to you. I'm saying here 0 is like x is stuck between 0 and 1. Here x can be stuck between minus 1 and 0. But yeah, there's going to be a lovely pattern which forms here. It's not easy to see, don't get me wrong. When x is between minus 1 and 0, what does mod of x do? Well, it just becomes, it's far easier to work it out if you just do this, yeah? When x is less than 0, mod of x is just going to be equal to minus x. Do you see what I mean by that? Because let's say x is minus 3. Yeah, mod of x is obviously 3. Well, that's the same as minus 3. So one way of dealing with this is to say f of 3 of x is going to be equal to. Now we know x is definitely negative. We can say it's the same as minus x, and it's only mod of x which can be replaced with minus x, remember? So this is going to become minus x plus x. Great. When I saw that, I'm like, oh yeah, I get it now. Plus x, yeah, I can't swap that. It's only modulus. Is that becomes 0. And so, in other words, when you're between 0 and minus 1, yeah, this is always mod of x when this is odd. And I think when it's even, it's always 0. Yeah. And so now we've cracked it basically. I can prove to you as well. Let's say we're doing f of 4. Yeah. Once again, we can replace when you're between 0 and minus 1. I hope you're convinced about my argument on the right hand side that would just become 99x. But like when you're between 0 and minus 1 here, just think about what you're going to get. You're going to get a mod of x which is going to turn into a minus x, a plus x. That's going to be 0. Then you have like plus x. You've got this like nested thing going on, plus an x in a mod. Yeah, that's basically f of 4. That becomes 0. Yeah, but then you've got mod of x again, but then we can make that a minus x plus an x, which becomes 0. And so that always equals 0. The even ones are always going to be 0. The odd ones are always going to be just like y equals minus x, basically. They're going to be like the left-hand side of a normal modulus graph. Yeah. Now I can do it because I realize that f of 99 is just going to be the same as basically this, where this is like 1 and 1, and that's a half. But on this side, it's going to be like a really steep line, y equals 99x, and I'm going up to 1. So as y is 99x, that must go up to 99. And so this is 1 times 99 times a half, which is like 49.5. Add them together, and I seem to get the answer in the answer key of 50. Yeah. Um, if you don't understand that one, it's well worth looking at it on Desmos or GeoGebra or something like that. You can see the graph kind of change quite nicely. ABS is the way you put in a modulus on those kind of graphing software packages. But yeah, they were difficult. Those two I found harder than the first two I did. I like 20. I found 19 frustrating, but also illuminating. Be careful with square roots. Be careful with square roots. Okay, good luck, James, tomorrow. Hope it goes really well. Bye bye.